So today we're going to talk about exponential growth and decay, and what this is kind of the end of our journey into talking about exponential growth and decay, and talking about compound interest, that kind of stuff. So the whole kind of reason we really started the conversation with compound interest was to eventually get to this formula for continuously compounded interest, which was the amount of stuff you have after time up to t years is equal to PE to the RT power. But the point of that really was so that we could actually talk about this other kind of more general formula. And all I want to say right this moment is that these two formulas, A equal PE to the RT and Y of T equal to CE to the KT, or just Y equal to CE to the KT, those are the same formulas. Yeah, people have used different letters for things, but they still represent the same stuff. Here, A is the amount of money you have after so much time. Here, Y of T is the amount of stuff you have after so much time. Here, P is the principal that you're starting with. Here, C is your initial amount of stuff, your beginning value, your initial population, or the initial amount of radioactive material you have. E is still E, approximately 2.7. Here, R is the interest rate. Here, K is more just generally the rate of growth, which we'll talk about more about how you find K. And then lastly, T is still T, time. So these two equations really are the same. People just use different letters for them. And there's lots of different versions of this formula. Some people, I don't really need you to write this down, but some people like to write something like, there's a couple different variations. Some people write something like N of T equals N naught times E to the KT. Same deal. It's just the same formula with different names for the constants. So I want you to be comfortable, familiar with the fact that all these formulas are really kind of the same. If you have a constant times E to a constant times your variable, that's a model for exponential growth or exponential decay. I'm going to say it one more time. These two formulas, all formulas like this are the same, and they're all models for some sort of exponential growth or exponential decay. So when we were talking about continuously compounded interest, the money we were compounding, or the interest we were compounding, was growing exponentially. Kind of neat. So let's go ahead and get to it. Let me get very disorganized over here. Sorry. Where are my notes? It was good. Where are my notes, actually? Hiding things from myself, as usual. For real. Where are they? Oh, there we go. Okay. So I'll make sure I'm not like forgetting anything. Sure. Okay. So, see what we got. Exponential growth occurs when the population grows at a rate proportional to its current size. And that is actually the hallmark of what it means for something to be growing or decaying exponentially. It is growing proportionally to the population size. So as the population increases, the rate of growth also increases, because if there are more people, they can make more people faster. Or if there's more bacteria, they can make more bacteria faster, right? For example, 4% per each year. Growth with time becomes an exponential function, and it occurs in many different real life scenarios. So we can think about human populations growing exponentially, and that's true up to a point, right? There's some capacity issues eventually, but a lot of the times we do model human population growth with an exponential function. Or bacteria definitely grow exponentially. Radioactive substances decay exponentially, right? They decrease in size. What else is there? Atmospheric, this one I always forget about. Atmospheric pressure, as you increase in elevation, apparently has exponential decay, which that's something that's kind of always like, oh yeah, I forget about that. And then of course, what we talked about last class, interest compounded continuously grows exponentially. So here is the model for exponential growth and or decay. Sometimes people write this without the T there, so they just write it as Y equal to C e to the KT. Or sometimes they'll use C e to the K times X, right? Sometimes it makes more sense to use an X variable versus the T variable. Just to point out what everything is, you already know. You remember what we did last class, you know what I'm about to write. C here is instead of the principal, it's the amount we're starting with. So it's the initial amount of whatever stuff. So it's the initial amount of people, or the initial amount of radioactive substance, or the initial amount of bacteria, et cetera, et cetera. K is what's called the growth rate. Now, we are going to have to be a little bit careful about K, because for example, if you said the population was increasing by 4% each year, K isn't actually going to be 0.04. There's a more complicated calculation after you figure out what K is. And then, of course, as is typical, T is time. And then Y, of course, is the amount of stuff you have after T amount of time. So amount of stuff after T units of time. I say T units of time instead of T years because now that we're moving on to a more general model here, you measure the time units can be measured in whatever you want. So you can do seconds, minutes, hours, weeks, months, days, whatever you're being told. So if someone says we're measuring this in months, then you're going to use months. I should also point out, I imagine many of you have seen this formula in some context before, potentially chemistry, potentially just other math classes. Some people, when they write this formula, like to distinguish between exponential growth having a positive K times T and exponential decay having a negative K times T. I'm not going to do that, and I don't really encourage that because here's what's going to happen. Whenever we are in an exponential growth situation and we have to find that K value, it's just going to end up being positive. And whenever we're in an exponential decay situation and we have to find that K value, we're going to end up getting a negative value right off the bat. Like we're not going to have to do extra work to make it look negative. So I'll remind you when we get there that, oh yeah, that's a negative number or that's a positive number. But that's what I will say is you don't need to slap on a CE to the negative KT if you know you're talking about exponential decay. You certainly can. If that's the way you've done it in the past and you'd like to make it that way, totally fine. But I'm going to recommend not doing it that way. So let's look at some examples. For example, consider a medical researcher studying a newly discovered species of bacteria. That sounds terrifying. Let me put this right here. At time zero, the beginning, she puts 100 bacteria into a favorable growth medium, like a petri dish. Its growth follows the equation y of t equals 100 e to the 0.25 times t, where t is in hours. At this point, we're just going to write down a few numbers to kind of see what we get. So at time zero, if you actually were to plug in 0, you would get 100 times e to the 0.25 times 0. And this is something I encourage you all to kind of take to heart because it's going to come up often. When you plug in 0 to this equation, 0.25 times 0 is 0, and e to the 0 is 1. So typically, whenever you plug in a 0 to an exponential growth or decay, you just get e to the 0, which is 1, and then times the initial value, which is why it's the initial value, because at time 0, that's how much you're actually going to have. So if I simplify this, that's just 100 times 1, which is 100. I meant to bring my calculator, and I think I left it in my office. Stupid phone calculators I'm stuck with today. It's terrible. Okay. Fortunately, I've written out most of these numbers, but occasionally, Let's look at the next value. If I plug in 1, I'm really just substituting this into the equation. So I'm going to get 100 times e to the 0.25 times 1. And then I can't really do anything else with that without a calculator. So if I use the calculator to get an approximation, that's going to be approximately 128. And then if we do it again for the next one, y of 2 is going to be 100 times e to the 0.25 times 2, which I suppose we could simplify and say that's 100 times e to the 0.5. And if we use a calculator, we get approximately 212. Sorry, not 212, 165. 212 is the next one. And finally, if we plug in 3, so 3 hours later, we're going to have 100 times e to the 0.25 times 3, which is 100 times e to the 0.75, which is approximately 212. Here's what I want you to see from this right now. This relationship is not linear. Every time we increase the time by 1 hour, we increase the population by an ever increasing amount. So from time equals 0 to time equals 1, our amount of bacteria is increasing by about 28 bacteria, or 28 bacterial cells, I guess. From time equals 1 hour to time equals 2 hours, we're increasing by about 37 cells. From time equals 2 hours to time equals 3 hours, we're increasing by about 47 cells. So every time we go another hour, the amount we are increasing by is more. And that is kind of what it means to be growing exponentially, is that every time you keep moving on and on, the amount you're increasing by is also increasing. And then if you go all the way down to say like 24 hours, so 24 hours later, y of 24 is going to be 100 times e to the 0.25 times 24. By the way, 24 times a quarter, or 1/4 of 24 is 6. This is 100 times e to the 6th power, which is approximately big, 40,403 bacteria. Right? So that's getting very large, very fast. And again, that's what really, when I think of exponential growth or decay, we're thinking of things really, really taking off as time goes on, just for a little bit. Like, so when you're thinking about exponential growth or decay, if this is time, and this is the amount of stuff, the growth starts off kind of slow, right? We're not increasing that fast at the beginning, but then you get this rapid increase. We don't have a vertical asymptote, right? You can keep plugging in larger and larger and larger, or later and later and later values of time. So the values you keep getting bigger and bigger, but you can always keep going to the right. So here at the beginning, we kind of grow slowly at first, but then at a later time, we have really, really rapid growth. So that is what you should be thinking of. If someone says exponential growth, you're like, okay, well, it might start off kind of slow, but eventually it's going to just zoom away off into the stratosphere. Or if you're having exponential decay is a little bit different, right? You kind of decay. Yeah, it's actually kind of the opposite. You can kind of start decaying fast and then you flatten out. So exponential decay actually has kind of the opposite behavior, whereas the decay starts off really rapid and then slows down, which is why when you talk about like radioactive materials, when you talk about how long they take to decay, that's why they take so long, because eventually you get out to this tail end where you have just a little bit, but it takes so long to get to the next little bit. Yeah. So let's look at some actual examples here. Oh, for those of you joining, okay, so notes. All right. So here's what I want to say about all these kind of exponential growth decay problems. And you'll see these later on when we take calculus as well. They're almost always kind of, well, actually, let's do an example and then I'll say things. So let's see what we've got here. A colony of bacteria is growing exponentially in a petri dish. Initially, there are 40 bacterial cells. 2 hours later, there are 120 bacterial cells. Find the behavior model of the growth of the bacteria. In other words, find C and K. So if someone says find the model, we already know we're starting with y equals c to the k t. So we have y equal to c e to the k t. And our job, first and foremost, is to find out what c and what k are. I am a big fan of writing down the following sort of thing. I like to make a table. It's a really kind of simple table. I'm going to make a table of time values or input values on the left and y values or output values on the right. So then I'm going to write down what I know. I know that there are 40 bacterial cells initially. So at what time do I have 40 bacterial cells? Time 0, right? If they say initially, that means you want to say that's time 0. Even if it's a year, like if I said in 1960 I had 40 bacterial cells, I'd be like, okay, 1960 is time equals 0. And then whatever the next time was would be whatever unit of time made sense. So like 1963, I'd be like, oh, t equals 3. So here at time equals 0, I have 40 bacterial cells. And then 2 hours later, so time equals 2, I'm going to have 120 bacterial cells. And then I'm going to use each of those data points to find what C and K are. It is very typical to have, if you have a 0 and something, use that one first, because that's going to make it really, really easy to find C. In fact, I don't even feel like you really need to show this next step. I'm going to show it. But if I plug this in to my equation, I'm going to get 40 on the left equal to C times E to the K times 0 on the right. K times 0 is 0. And e to the 0 is 1. So really what I'm getting is C equal to 40, which makes sense because C is always the initial value. So if you know you're starting with a value of 40 bacteria, then we should automatically just be able to say, oh yeah, C equals 40. So you can totally show this work, but you do not have to show this work in general because it's pretty well known. So we've got C equal to 40. Great. Now we're going to use that in conjunction with the other data point to find out what K is. So most of the time, with a couple of exceptions, but most of the time you have to find C before you find K. So now let's find K. I'm going to plug in this data. Also, I'm going to plug in C equal to 40. So I'm going to have 120 equal to 40 times e to the K times 2. And now our job is to solve for K. This is very much like solving for T in the exponential growth, or in the problems we were doing last class with the, oh my gosh, the interest. So it's very much like solving for something in the exponent. We're going to do the same thing we did last time, which is try and solve for this by first getting rid of 40. So divide both sides by 40. Sum of 120 divided by 40 equal to 40 e to the, I'm going to say e to the 2 times K divided by 40. 40 divided by 40 is 1. So then I have 3 on the left equal to e to the 2K. Take the natural log of both sides. So the natural log of 3 equals the natural log of e to the 2K. Eventually, we're going to get comfortable enough with saying, oh, if you have the natural log of e to the something, it's just going to be the something. The natural log of e to the 2K comes down, and then 2K times natural log of e is 2K times 1. So we have the natural log of 3 equals 2K, or K equals the natural log of 3 divided by 2. So finally, plugging both of those things back into our original model, we have that our model is actually y equal to 40 e to the, it's a little bit gross to write down, but we'll say natural log of 3 over 2 times t. That's our model. C and K found. So whenever anyone is asking you to do something with an exponential growth or decay sort of problem, usually the first things you have to do are find C and find K and get the actual full-fledged model before you can answer any questions that they're asking you. So great, now we've done that. Now let's look at part B. How many bacteria are there going to be in 5 hours? So what I'm going to do is I'm going to say, well, what am I setting equal to 5? Am I setting y equal to 5 or t equal to 5? Right, it's a number of, it's a measure of time. So we're going to set time equal to 5 and solve for whatever's left over. Here's where I'm going to say the thing. So typically, when you're doing these sort of exponential growth or decay problems, the first thing you're going to do is, like we just did, you're going to find C and find K so you can find the model. And then after you have found the model, there's really only 2 kinds of questions we can ask. I can either say, how much stuff do you have at a certain time, like I'm asking right now, or what time is it when I have a certain amount of stuff, like in the next question. So I can either give you an amount of bacteria and ask you how long it took me to get that many bacteria, or I can give you an amount of time and ask you how much bacteria do I have after that amount of time. But really, it's always I can give you this information and ask for the other thing, or vice versa. And that's really kind of, with some exceptions, that's really mostly all we can do. Is just say, here's the time, tell me the stuff, here's the stuff, tell me the time. When I do this, I kind of like to throw it back into the table. So if I'm thinking about my table here, I'm thinking, okay, I've got time equal to 5, and I'm trying to find out what y is. Okay, so I'm just going to use my model. So my model was y equals 40 e to the natural log of 3 over 2 times t. And now I'm just going to plug in t equals 5, which is not going to be particularly nice. So plugging it in, we're going to get y equal to 40 e to the natural log of 3 over 2 times 5. And I will tell you, if you're taking a test and someone is not allowing you to use a calculator, this is where the process ends. We're done. We can't really do anything else here. So without a calculator, this is our final answer. This is our exact answer. Now, if we wanted to get a good idea of, so looking at that number, I don't know how many bacteria that is. Right? I mean, I don't know what e to the natural log of 3 over 2. So I should use a calculator just to get an idea of what's actually happening here. So if we plug into a calculator, we get approximately 624 bacteria. But I will tell you, this is the actual answer. And this is just the approximation. So if someone says to give them an exact answer, they mean this first thing, not this second thing. Even though the second thing is more useful. Okay, let's do the last part and then we'll have to sneeze. That's terrible. I hate the having to sneeze but not sneezing feeling. Awful. Okay, so the other question is, how long does it take this population to double? So now, if we're thinking about our table, we're being given the y value, right? We're being asked how long it takes until the population gets to how much. It's a good question. So when I say double, right, you want to double the initial value. You can actually technically double any value and it'll work out. You just have to be careful, but it's easiest to just say, I'm going to take my initial value and double that, because then the time I'm looking for will just be the time elapsed from 0 to whatever I get. So you could totally do it from you could double 120 and say set it 240 and then get the time and then subtract off 2 hours to get the actual amount of time that elapsed. That seems like more work than I want to do. So you should always double the initial amount. So double the initial amount. Or whatever factor of the stuff you have. So if they said how long it takes, triple. So here we don't know how long it takes. That's what we're trying to find. And the amount of stuff is going to be 80 bacteria. And this is where it's good to think about the sense of what's happening. So I definitely expect that it's going to take less than 2 hours. Because in 2 hours, the population shot all the way up to 120. So I should definitely get to 80 before I get to 120 if the population grows. All right, so now we do the math. So I'm going to set 80 equal to 40 e to the natural log of 3 over 2 times t. Solving for y is always pretty much straightforward. You're literally just plugging in the t value and getting the answer. Solving for t is more work. Just like solving for k is more work. We have to do the whole thing where we divide both sides by this. I'm going to have 80 divided by 40 is 2. 40 divided by 40 is 1 times e to the natural log of 3 over 2 times t. So this is where it's going to pay. Oh, I'm doing something here. This is where it's going to pay to not write everything out. Meaning, I'm going to take the natural log of both sides, and I'll write it out. I'll write it out one more time. So I'm going to say the natural log of 2 equals the natural log of e to the natural log of 3 over 2 times t. That feels terrible. But here's what I want for you. I want you to know that if you're taking in the natural log of e to some power, e to some stuff, you're just going to get this whole power. Because the power will come down and will multiply by the natural log of e, which is just 1. So whenever you're doing this sort of thing, and you're taking the natural log of e to the something, you can just go straight to saying, oh, I'm going to get the natural log of 2 equal to the natural log of e to the stuff is just the leftover, or I should say the stuff that's in the power. Which isn't too terrible as far as doing calculations. Now we want to solve for t. And instead of dividing by a fraction, I really don't want to divide by the natural log of 3 over 2, although you certainly can. Right? You could definitely be like, okay, I'm going to say that the natural log of 2 over the natural log of 3 over 2 is equal to t. I would not leave my answer like that. And instead of doing that, I would say, let's multiply both sides by 2. So I have 2 times natural log of 2. And let's divide both sides by natural log of 3. Which is totally what you would get if you took this expression and flipped and multiplied the bottom part. Right? If I flipped the bottom part, I'd have 2 over natural log of 3, which is exactly right. And then, if you want actually meaning, We say that's approximately, if I plug that into a calculator, it's going to be approximately 1.26 hours. So about an hour and 15 minutes. Right, not 26 minutes, because 2.26 minutes is about a quarter of an hour, which is about 15 minutes. Questions so far? About anything. I mean, about anything related to it. Probably not. All right, so here's what I'm going to say a lot. This process never really changes. It's always the same steps kind of over and over and over again. So if you see something where they say you have something growing exponentially or decaying exponentially, you automatically want to think of, there's my model. Find C and K, plug in whatever they're telling you, define whatever they're asking. Those are kind of the steps. I mean, not kind of, those are the steps. So let's do some more practice. Written all over this thing, unfortunately, here. Let's see, can I keep things in order? Maybe, maybe not. I'll figure it out later. So, radioactive waste is often dumped in the middle of the desert and left to decay, which just sounds terrible. I guess that's where it goes then. The 12-gram sample of radioactive substance decays to 10 grams in 25 days. How long will it take for half the substance to decay, also known as the half? One note about this, and I want you to all be extra careful around the language of these problems. Sometimes people like to be super tricky about this. So sometimes they write it decays to 10 grams. Sometimes they write it decays and you're left with 10 grams. Sometimes they write something terrible and they say decays by 10 grams, which means you've lost 10 grams and you actually only have 2 grams left. So just make sure that whenever you're doing these decay problems, you're reading carefully and you're asking yourself, okay, how much stuff do I have? Because we're always talking about how much we have, not how much we've lost. How much stuff do you have after whatever length of time has passed? Okay, so let's write down, well, I know it's let's see, I know it's radioactive decay, right? Actually, they haven't actually said those words here. Yeah, but you should always assume if you're talking about radioactive substances that they mean it's decaying exponentially. That is the normal assumption. So we're going to make the assumption of the usual model that y equals ce to the kt. I will point out that in some textbooks they like to use specifically lowercase m of t equals m naught e to the kt, where lowercase m stands for the mass that you have. So just be aware, right? There's totally different ways of writing it, but we're just going to stick with this because it's nice and easy. And it'd be totally fine to use either one. All right, let's make our table. In fact, I want you all to fill in the table. You've got times and you've got amounts. You should have 2 distinct times going along with 2 distinct amounts. I'll even give you the times. Time measured in days, amount of stuff measured in grams. Not going to happen. All right. So how many grams do we have at day 0? 12 grams. All right. How many grams do we have at day 25? 10. Because we decay to, not decay by. Just be careful. And then finally, I like to make a third line on my table typically, because usually there's one more piece of information. I should say there's like half of a piece of information. There's the question they're asking, which is in this case, how long? So they're asking me for the time. Right? They're asking how long. So I don't know what time it's going to be. That's what I'm going to try and find. How long until, or how long will it take for half of the substance to decay, also in the half-life? So we're asking how long it's going to take to get from 12 grams to how many grams? Right, half of what you started with. I highly recommend making this table every time you do these problems. I find it really helps me organize my thoughts. So we're going to find all the things. Now you could totally just say right off the bat that C is going to equal 12. But if you don't want to, you can also do the work. You can plug in 0 and 12. Say, okay, if I plug in 0 and 12, I'm going to get 12 equal to CE to the K times 0. And then we're going to get E to the K times 0 is E to the 0, which is 1. So you have 12 equal to C times 1, which means C is equal to 12. Great. But again, you're totally welcome and encouraged to bypass that work. If you're comfortable saying, oh yeah, I know we're starting with 12 and C is the starting amount, you're totally fine just to jump straight to Y equal to 12 E to the KT. That's a perfectly fine jump. Right, I'm plugging in my value of C so that I can refine or update my model. Because the goal, at least the goal at this point, is to write the fully fledged model with an actual number for C and an actual number for K. So now our job is to find K. So we're going to use the other data point. It always goes like this. You're always plugging in the first thing, typically finding C, plugging in the second thing, typically finding K, and then plugging in the third thing to find whatever they're asking to find. So here, I'm going to plug that in. I'm going to get Y is 10 equal to 12 E to the K times T is 25. And now we're going to solve for K, which is always going to be the process of dividing by your coefficient and taking the natural log of both sides. I do recommend not writing this as a decimal unless it's easy to. So for example, if you happen to get 6 divided by 10, you can totally reduce that to 3/5 or write it as the decimal 0.6. Either way is fine. But if you have a repeating decimal forever, I really recommend just writing it as a fraction. So here, I'm just going to divide both sides by 12 and write 10/12 equal to E to the 25K, which you can totally reduce 10/12 to 5/6. So taking the natural log of both sides, I'm going to say, oh, that's 5/6. So I'm going to have the natural log of 5/6 equal to 25K, right? Because I took the natural log of both sides. Take the natural log of both sides. And I didn't show the work of saying that the natural log of E to the 25K was 25K times the natural log of E, which is 25K times 1. I want you to get comfortable with saying, oh yeah, the natural log of E to a thing is just the thing. And now we're almost done solving for K. We're going to divide both sides by 25. So K is going to equal the natural log of 5/6 divided by 25. Something to be careful about, that 25 can't creep into the natural log, right? It is definitely on its own. It's not the natural log of 5 divided by 6 times 25, right? That 25 is outside of the natural log. So it's the natural log of 5/6, pause, and then divide by. All right, so now we have our model. Our model is Y equal to, let's see, my C value is 12. My K value is this gross thing here. Natural log of 5/6 over 25 times T. That is our model. But that's not the end of the story. Because after you find the model, then we're being asked to find the half-life. So whenever you're asked to find the half-life for exponential growth or decay, I should say, whenever you're asked to find the half-life for exponential decay, right? It's not a thing, right? For exponential growth, you'd be asked to find the doubling time. The half-life is just how long it takes for half of the stuff to remain and half of it to decay. So let's see here. Finding that, I'm going to set Y equal to 6. Half of what we started with. So we're going to get 6 equal to 12 times E to the K times T. Here's something that's going to happen every time you find a half-life when you do this process. The first step, you're going to divide both sides by 12 or whatever the number is there, and you're going to get a half on the other side. If you're finding the half-life, you should always end up with 1/2 equal to E to the K times T. That is always going to happen. In fact, if you've taken chemistry before, you might know that there's a formula for the half-life, which is that it's the natural log of 1/2 divided by K. I don't expect or need you to memorize that, but if you're aware of it, it's a true thing. The half-life can always be found by doing the natural log of 1/2 divided by K. Now, even if you do know that, I still expect you to show the work of finding the half-life. So knowing it's a good check, but I still want to see the work for having actually found it. So let's see here. I'm going to take the natural log of both sides again. I know that on the right-hand side, the natural log of e to some stuff is just the stuff. So I'm going to get the natural log of 1/2, taking the natural log of the left side, equal to the natural log of e to the all this is just the all this. So it's the natural log of 5/6 divided by 25 times t. I'm going to show the work for the next step though, because I feel like I kind of glossed over it last time. So to get t by itself, I recommend doing the following. I recommend taking this equation, which I'll write again, and saying I have natural log of 1/2 equal to the natural log of 5/6 over 25 times t. And I definitely recommend multiplying both sides by 25. Because 25 divided by 25 is 1. So I have 25 natural log of 1/2 equal to the natural log of 5/6 times t, and then dividing both sides by the natural log of 5/6. So natural log, so something divided by the same something is just 1. So I end up with t equal to, this can't be simplified really, 25 natural log of 1/2 divided by the natural log of 5/6. Yes, it's not a lovely number, but it is the correct answer. So that's how many days it would take for half of the substance to decay. Just so we have an idea what that actually is. Ooh, here's a good question. So why can't they keep track of anything? Yeah, there we go. Papers everywhere. So this question, I hope this question shouldn't be too hard to answer, I don't think, but do we expect the half-life to be more than 25 days or less than 25 days? Definitely more. How about more than, I wonder if it's more than 50. So here's the question I'm going to ask. Well, here's the, actually, I'm not asking. So I want to point out that if you're asking if I ask the question, how much stuff do we have after 50 days? The answer would not be 8. It's not a linear relationship, right? The same amount of time changing doesn't correspond to the same amount of change in the amount of stuff you have. So if you want to know how much stuff you have after 50 days, it would be a totally different thing. It's kind of interesting. It would actually be, no, I don't feel that. There's something cool and interesting here, but I don't think it's particularly useful. So I'm not going to say it, even though I really, really want to. So refrain from saying all the things. Try to. But I was going to tell you what the actual number was. Wow, papers. This is approximately 95 days. So it takes, yeah, okay, that's all right. The interesting thing about exponential growth and decay, in my opinion, is the same kind of growth factor happens in the same amount of time. So what this means, this 95 days being the half-life, is that every 95-day period, you cut your stuff in half. So from time equals 0 to time equals 95 days, you're going to have to go from 12 to 6 grams. And if you went for another 95 days, you'd be down to 3 grams. If you went for another 95 days, you'd be down to how much? Half of 3, right? You have 1.5 grams. So the thing about exponential growth and decay is the amount of time always multiplies the amount of stuff you have by the same amount. That's why when we talk about exponential growth, we talk about the doubling time. So in the US population, the doubling time is about like, I think 40 years maybe. So it means every 40 years, the population doubles. Now, I know it's not exactly exact, but that's the idea, is that it's this same amount of time, the population multiplies by the same factor every time. That's kind of the unique thing about exponential growth or exponential decay. Kind of interesting. Okay, I think I got another example or two here. Maybe if I can, wow. I've just like thrown papers everywhere. Okay, here we go. All right, here we go. Found them. Good. All right. Example. 2 months ago, you had 3 mice. Sounds like a bad idea. Now you have 18 mice. What will the population size be in 2 more months? The population of mice is growing exponentially. This one is kind of funky in that we're not actually starting with the time equals 0 kind of thing. And again, really get organized with everything. But I'm still going to make my same sort of table. So if you can, I think it's always a good idea to let your beginning time, whatever the most ancient time long ago is, make that your time equals 0. So 2 months ago, actually give myself more room. So 2 months ago, I want to make that time equals 0 because it's convenient. 2 months ago, I had 3 mice. And then now, so if 2 months ago is time 0, what time is it now? 2, right? It's 2 months later. I have 18 mice. What will the population size be in 2 more months? 2 months later, which will be time equal to 4. So it is usually in our best interest to kind of start at time equals 0. You can do different things. It will make it more challenging. Yeah. Okay, so now here's where the thing I said before, I actually want to say more strongly. In the 2-month period, what's the population getting multiplied by? 6. In another 2-month period, and we're going to see that we're going to do all the work, but I'm going to tell you, we're going to expect the population to multiply by the same factor. So every equal period of time multiplies the population by the same amount. So if you take a 2-month period and you multiply by 6, another 2-month period will multiply by 6 again. And another 2-month period will multiply by 6 again and again and again. So we're expecting to get 6 times 18, which is 108 mice. Which is too many mice. Don't want that many mice. But let's do the work. So usual deal. We're growing exponentially. Here's our model. Y equals C e to the kt. Everyone, what should my C value be? 3, totally 3. C equals 3 for sure. Just from this first piece of data here. So then we've got Y equal to 3 e to the kt. And now we're going to find K. So let's see here. I'm going to plug inside the piece of data. I'm going to get 18 is Y equals 3 times e to the k times 2. Divide both sides by 3. We get 6 equal to e to the 2k. Take the natural log of both sides. Natural log of 6 equals the natural log of e to the 2k, which is just 2k. Finally, k is equal to the natural log of 6 divided by 2. Cool. So now let's rewrite our model. Our model is going to be y equal to 3 e to the natural log of 6 divided by 2 times t. Great. Now let's see what happens when we plug in time equal to 4. And this is where we're actually going to be able to do this without a calculator, which is kind of cool. And this is actually generally true. If your interval of time is kind of a, I don't want to say this. No, I don't really have a good way of saying it. No, if your interval of time is like a multiple of your kind of initial length of time, so like our initial length was from 0 to 2, so our initial length of time was 2. If our actual time is a multiple of that, this becomes easy to solve. Here's what I mean. If I plug in t equals 4, I'm going to get y equal to 3 e to the natural log of 6 over 2 times 4, which doesn't look great, but it is not terrible. So let's see what we get here. One could use a calculator, but we're not going to. So we're going to get, well, what's 4 divided by 2? That's going to be y equal to 3 e to the natural log of 6 times 4 over 2 is just really 2 times the natural log of 6. I'm just saying 4 divided by 2 is giving me 2. And now I'm going to use a rule for logarithms. It says, well, ignore all that for a second. If you have 2 natural log of 6, I can put that 2 up in the exponent. That's a totally valid thing to do. So I could totally rewrite, I'm going to try and make this look cool here. I can totally rewrite that part as the natural log of 6 squared. Right? That's a totally the same thing. But then the base is still there. So what I really have is y equal to 3e to the power of the natural log of 6 squared. All I did was rewrite the power. Instead of 2 natural log of 6, it's natural log of 6 squared. All right, now here's where one of those homework questions is going to come back. What's e to the natural log of 36? 36. Right, so one could say, although I would not choose to say, the e to the power of the natural log cancel each other out. I would encourage you to instead think of it as they undo each other. You have e to a power. The power that if you raise something to that power, you get, if you raise e to that power, you get 36. That's what natural log of 36 really says. Right? The natural log of 36 is e to some power equals 36. I've got e to that power. It equals 36. It kind of feels like I'm just saying words in a circle, but I'm really not. I know it kind of feels that way. It always feels that way. So what we really have here is y equal to 3 times this number here is 36. And 3 times 36 is 108. So it's kind of a neat fact that if you know the population multiplies by 6 every 2 months, then if you just go another 2 months, it's going to multiply by 6 again. And if you went another 2 months, it'll multiply by 6 again, and so on and so on and so on. So if you happen to have an amount of time that is a nice multiple of your initial kind of interval of time, you can do this easier calculation. Now, you could also have just left it like this and said, oh, I have e to the 3e to the 2 natural log of 6. And if you threw that into a calculator, you would also get approximately, you would get 180. Yeah. So I do want everyone to be reminded of, I got time, the fact that if you have in general, so just as a reminder here, if you have e to the natural log of anything, it's just going to equal the anything. Important thing that comes up quite often. All right, let's do this last example because you do want to see it. Okay. Find the half-life of a radioactive material if after 3 years, 20% of the material has decayed. All right, so write down our table, the times and amounts. The time 0. How much do I have? They didn't tell us. Not nice. So here's actually, this is wonderful. If they don't tell you how much you have, that's kind of like the best situation ever. Because you can make up any number you want. I like to say at time 0, I have 100 grams. You might like to say you have 100 pounds, or you might say like to have 100%. You can use whatever number you like, but I encourage you to use 100 of something. Because 100 is very easy to take a percentage of. So I'm going to say time equals 0. I have 100. You don't even have to put a unit. You can just say you have 100. And then 3 years later, okay, be very, very careful. If I did start with 100 grams, if you read the question carefully, 3 years later, how much do I have? I have 80 grams. So 20% of the material decayed, meaning 20% is gone, and I have 80% left over. And then they're asking me to find the half-life. So I want to know how long does it take until I'm left with half of what I started with, which is 50. Okay, so usual process. We know we're going to get C equal to 100 because of this first thing here. And then we have Y equal to 100 E to the KT. We're going to use our second data point to find K. So we're going to have Y, oops, not Y. I'm plugging in 80 for Y. We're going to have 80 equal to 100 E to the K times 3, which is going to be, if I divide both sides by 100, I have 80 divided by 100 equal to e to the 3k. This is a place where I probably would choose to use a decimal. Right? You could totally write 80 divided by 100, that reduces to 4/5, or you can just say it's 0.8. I think that's probably nicer. So I'm going to say 0.8 equals e to the 3k. You're totally welcome to use a fraction. And then the natural log of 0.8 equals 3k. So the natural log of 0.8 divided by 3 is equal to k. And then we get our model. Model is 100 times e to the k t. And then we're going to solve for the half-life. So we're going to plug in our last data point and solve for t. So plugging this in, we're setting y equal to 50 equal to 100 e to the natural log of 0.8 over 3 times t. Divide both sides by 100. So we get 50 over 100, which is 1/2 or 0.5, whichever you like, equals e to the natural log of 0.8, 3 times t. Then we take the natural log of both sides. So we have the natural log of 0.5 equal to the natural log of e to the stuff is just the stuff. So it's the natural log of 0.8. Oh, sorry, thank you. Divided by 3 times t. And then finally, we solve for t by multiplying both sides by 3 and dividing both sides by the natural log of 0.8. So that's our actual exact answer. And then if we use the calculator, we get approximately, oh, did I not write it down here? I don't know because I don't have a calculator on me because I planned poorly. I guess I have a calculator. So that's it. That's all I got. But let me find this value for you so you can actually have it. I mean, you don't have to stick around for this, but I want to know because I want to know. So we take, let's see. It's always a challenge here. Can I do it? Maybe. I don't know. This calculator is not my favorite. The 0.5, take the natural log of 0.5, divided by. Seems plausible. Yeah, that seems reasonable. I got about 9.31. Which seems reasonable because so here's what I'll say. You can totally take off, leave whatever. But here's what I'm going to point out to you. Every 3 years, we're going to have 80% of what we had before. So after another 3 years, 80% of 80 is 64%. And then after another 3 years, 80% of 64% is 51.2%. So yeah, that seems totally legit, right? After 9 years, we're just a little more than 50%. So it seems like 9.31 years is a totally reasonable expectation for what the half-life is. Kind of cool. All right, that's all I got.